In this video on Fourier series, we will discuss generalized rule of obtaining integration by parts, which is quite useful in finding Fourier series. Secondly, we will discuss Dirichlet's conditions, which need to be obeyed by the functions whose Fourier series can be obtained, meanings of odd and even functions, their graphs, and some representative problems to understand these concepts. To integrate the product of two functions, one of which is a power of x, we can apply this generalized rule of integration by parts. In this, dashes denote differentiation and suffixes denote integration with respect to x. The rule can be stated as follows: integration uv dx equals uv1 minus u dash v2 plus u double dash v3 minus u triple dash v4 plus so on and so forth, where u and v are functions of x. Here, simplification should be done only when the integration is over. A thing to be noted here is alternate plus and minus signs appear. Plus sign, minus sign, plus sign, minus sign, plus sign, etc. Hello friends, welcome to channel Number Collage. This channel is dedicated to videos on a wide range of mathematical concepts and problems related to them, ranging from high school math to engineering math. Effort has been made to explain the concepts through basic mathematical ideas in a simple English. Hope you will like my effort. Thank you. For example, integral x square cos nx will be, here x square is u and cos nx is v. According to the generalized rule of integration by parts, this will be first function x square into integration of second. Integration of cos nx is sin nx upon n, then negative sign, derivative of x square 2x into 1 upon n, integration of sin nx minus cos nx upon n, now plus sign, derivative of 2x 2 into 1 upon n square, and integration of minus cos nx minus sin nx upon n. This will be x square upon n sin nx plus 2x upon n square cos nx minus 2 upon n cube sin nx. Please note, in this integration by parts, we have got only three terms because derivative of constant 2 is 0 and the terms 4th onwards will each be 0. At this stage, let us recall four important results. The first being sin n pi is 0. Number 2, cos n pi is minus 1 to the power n. Number 3, sin of n plus half times pi is minus 1 to the power n. And number 4, cos n plus half times pi is 0, where n is an integer. A function fx is said to be even function if f of minus x equals f of x. For example, x square, cos x, sin square x are even functions because x square is same as minus x square, which is x square. Cos x is same as cos of minus x equals cos x. Sin square x is same as sin square of minus x, which is minus sin x whole square, again sin square x. In each of these functions, after replacing x by minus x, the original function is retained. Graph of even function is symmetrical about the y-axis. Here, y-axis is a mirror for the reflection of even function. Let us draw graphs of some of the even functions. These three graphs are those of even functions and they are symmetrical about the y-axis, that is about f of x axis. Integral of even function f of x dx from minus pi to pi is 2 times integral f of x dx from 0 to pi. A function f of x is said to be odd function if f of minus x is minus f of x. That is, after replacing x by minus x, the function takes negative sign. For example, functions like x cube, sin x, tan cube x are all odd functions. This is because x cube after replacing x by minus x becomes minus x cube. That is, the function assumes a negative sign. Similarly, sin x after replacing its x by minus x becomes minus sin x, which takes a negative sign. Tan cube x also after replacing its x by minus x becomes minus tan x whole cube, which is minus tan cube x. Here it also assumes a negative sign. Graph of odd functions is symmetrical about the origin. Like below, we have drawn graphs of some odd functions. In each of these graphs, we observe that the graph is symmetrical about the origin in each case. Properties of even and odd functions can be easily understood by comparing even functions to a plus sign and odd functions to negative sign. So, product of two even functions and two odd functions is positive, and the product of even and odd functions is negative. So they behave exactly like plus and minus sign respectively. In my last video, we have seen Fourier series for a function fx is f of x equals a0 upon 2 plus summation an cos nx n from 1 to infinity plus summation bn sin nx n from 1 to infinity, and the Fourier coefficients first a0 is 1 upon pi integral fx dx from alpha to alpha plus 2 pi. Fourier coefficient an is 1 upon pi integral f of x cos nx dx, and the third Fourier coefficient Pn is 1 upon pi integral fx sin nx dx from alpha to alpha plus 2 pi. These formulae for Fourier coefficients a0, an and bn are known as Euler's formulae. Now we will see what will happen to the Fourier coefficients a0, an and bn if function f of x is an even function and when it is an odd function. When function fx is an even function, a0 will be 2 upon pi integral f of x dx from 0 to 2 pi. Cos nx being an even function, product of f of x cos nx will also be even, and an will be 2 upon pi integral f of x cos nx dx from 0 to 2 pi, whereas sin nx being an odd function, product of f of x sin nx will be odd and bn will be 0. So it is clear f of x is even function. There will be only cosine terms in the Fourier series, and when f of x is an odd function, a0 will be 0. Cos nx being an even function, product of f of x cos nx will be odd and an will also be 0, whereas sin nx being an odd function, product of f of x sin nx will be even and bn will be 2 upon pi integral f of x sin nx dx from 0 to 2 pi. So it is clear, in case of fx being an odd, there will be only sine terms in the Fourier series and no cosine terms and no a0. It should be kept in mind, Fourier expansion of fx in each case shall not be valid, given the fact that expressing any function fx as a Fourier series depends upon evaluation of the integrals 1 upon pi integral f of x cos nx dx and 1 upon pi integral f of x sin nx dx within the limits 0 to 2 pi, minus pi to pi, or alpha to alpha plus 2 pi. Accordingly, fx should be defined for every value of x in the same interval, that is, in the intervals 0 to 2 pi, minus pi to pi, or alpha to alpha plus 2 pi. Therefore, any function fx can be developed as a Fourier series f of x equals a0 upon 2 plus summation an cos nx n from 1 to infinity plus summation bn sin nx n from 1 to infinity, where a0, an and bn are constants, provided a f of x is periodic, single valued and finite, b fx has finite number of discontinuities in any one period, and c fx has at the most a finite number of maxima and minima. According to first condition, sin inverse x cannot be expressed as a Fourier series. This is because it is not a single valued function. As we know, sin inverse half is pi by 6, and also sin inverse half is 5 pi by 6 in the period 0 to pi. Because it is not a single valued function, in terms of curve of a function, if a function has a rectangular shape curve like this, here integral fx from 0 to pi is this area a and this width is pi. So this area will be a into pi, which is less than infinity or finite. Here, since fx obeys first Dirichlet's condition, it is absolutely integrable and its Fourier series can be written. Now consider function fx equals tan x, whose graph would look like this. In this case, integral f of x dx from 0 to pi by 2 will be integral tan x dx from 0 to pi by 2 will be infinite, because as x approaches pi by 2, area will be infinite, and since tan x is not absolutely integrable between its domain 0 to pi by 2, tan x cannot be expanded as a Fourier series between 0 to pi by 2. Same is the case with domain from minus pi by 2 to 0. In short, tan x cannot be expanded as Fourier series in the domain minus pi by 2 to pi by 2, because these integrals are not finite. According to the second condition, f of x has discontinuities finite in number in the given range of domain. In the first graph drawn here, there are two discontinuities. The first is here, because at x equals a, there are two values of fx. First is f1 of a and second f2 of a. Same is true for the second discontinuity at x equals b, because the value of fx breaks at x equals b from f of b here to say f1b to f2b here. So since there are finite number of discontinuities of this function, its expansion can be expressed as a Fourier series. In case of second graph of function fx, x equals c is a point of finite discontinuity, because the graph breaks at f1c here and f2c here. Therefore, in this case, expansion of fx as a Fourier series is possible. When we say that x equals c is a point of finite discontinuity, both the limits of fx, limit fx as x tends to minus c, that is the left hand limit, and limit fx as x tends to c positive, that is the right hand limit, both exist at such a point, Fourier series gives the value of f of x at x equals c, that is f of c equals the arithmetic mean of these two limits, that is half times limit fx as x tends to c minus plus limit fx as x tends to c plus. According to third condition, fx has finite number of maxima and minima in the range of given domain. To understand this, let us consider graph of function fx, which is in the form of sawtooth shape. In the domain of minus pi to pi, it has one minima, and in the domain of 0 to 2 pi, it has one maxima. Here, since fx has finite number of maxima and minima, function fx can be expressed as a Fourier series. So the third Dirichlet's condition is also satisfied here. Find the Fourier expansion of f of x equals x square in the interval minus pi to pi, and hence prove that number 1, pi square upon 6 equals summation 1 upon n square from 1 to infinity. Number 2, pi square upon 12 equals summation minus 1 raised to n plus 1 upon n square. 3, n square upon 8 equals 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so on and so forth. F of x equals x square. F of minus x equals minus x whole square, which is x square, which is f of x. Since f of minus x equals f of x, x square is an even function, and like we have seen earlier, Fourier coefficient b0 will be 0. So we have to find only a0 and an. First, a0 is 1 upon pi integral 0 to pi f of x dx, that is x square dx, 1 upon pi x cube upon 3, 0 to pi 1 upon pi into pi cube upon 3 minus 0, which gives a0 equals, cancelling 1 pi here, pi square upon 3. Next we find an, which is, according to what we have seen earlier, 2 upon pi, because x square is an even function, integral f of x cos nx, that is x square cos nx dx, 2 upon pi into, by using generalized rule of integration by parts, x square into integration of cos nx sin nx upon n minus derivative of x square 2x into this 1 upon n, and integration of sin nx minus cos nx upon n plus derivative of 2x 2 into 1 upon n into 1 upon n, 1 upon n square into minus 1 into integration of cos nx sin nx upon n. Derivative of 2 will be 0, so we have to stop here from 0 to pi. This will be x square upon n sin nx plus 2x upon n square cos nx minus 2 upon n cube sin nx from 0 to pi, which is 2 upon pi. Here sin n pi will be 0, so 0 minus 2 pi upon n square cos n pi is minus 1 to the power n minus sin n pi is 0 again minus 0 square is 0 here, 2 into 0 is 0 here, and sin 0 is 0. So this will be 0, which is minus 4 upon n square into minus 1 to the power n, same as 4 upon n square minus 1 to the power n. So this is an. Now we have the Fourier series x square equals a0 plus summation an cos nx from 1 to infinity. That will be x square equals a0 is pi square upon 3 plus an is 4 upon n square minus 1 to the power n, that we write 4 summation minus 1 to the power n upon n square cos nx, and from 1 to infinity. So this is the Fourier expansion of even function x square. For deducing this first result, we will substitute x equals pi in this Fourier expansion of x square. So So this will be pi square equals pi square upon 3 plus 4 summation minus 1 to the power n upon n square cos n pi, which is into cos n pi is minus 1 to the power n equals pi square minus pi square upon 3, which is minus 1 to the power n into minus 1 to the power n will be minus 1 to the power 2n upon n square equals 1 upon 4 into 2 by 3 pi square, which is summation minus 1 to the power 2n is 1 upon n square equals pi square upon 6, which is the deduction of this first result. For the deduction of this second result, we will substitute x equals 0 in this Fourier expansion of x square. So it will be 0 equals pi square upon 3 plus 4 summation into cos 0, which is minus pi square upon 3 equals 4 summation minus 1 to the power n upon n square. Cos 0 is 1. This will be minus pi square upon 4 3s are 12 equals summation minus 1 to the power n upon n square. Pi square upon 12 equals minus 1 summation. This will be pi square upon 12 equals summation minus 1 to the power n into minus 1 will be minus 1 to the power n plus 1 upon n square, n from 1 to infinity. So this is our second deduction. In order to prove this third deduction, we will write the first deduction and the second deduction in the expanded form and then add them together. So the first deduction in the expanded form is pi square upon 6 equals 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus so on and so forth. We will name this 1. Second deduction in the expanded form is pi square upon 12 equals 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square plus so on and so forth. We name this 2. We will add 1 and 2 together. Pi square upon 6 plus pi square upon 12 equals 1 upon 1 square plus 1 upon 1 square will be 2 times 1 upon 1 square. 1 upon 2 square minus 1 upon 2 square will be 0 plus 1 upon 3 square plus 1 upon 3 square will be 2 times 1 upon 3 square plus similarly 2 times 1 upon 5 square plus so on and so forth. This is upon 12. 2 pi square plus pi square 3 pi square equals 2 times 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so on and so forth. 3 ones are 3 fours are. This will be pi square upon 4 twos are 8 equals 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so on and so forth, which is the third deduction that we have to prove. Now we will see how to find Fourier expansion of a piecewise function defined as f of x equals, hence we have to deduce pi square upon 8 equals 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so on and so forth. First we will check whether fx is an even function or an odd function. For checking, we will replace x by minus x. So f of minus x will be, which will be pi greater than x greater than 0. As we know, when we multiply by minus 1, the inequalities get reversed. X plus pi by 2 minus pi less than x less than 0 because of the same reason, which is nothing but original function f of x, which implies that f of x is an even function, implies Bn equals 0. So we have to find only a0 and an. First a0, for even function it is 1 upon pi integral f of x dx from 0 to pi, which is, for this domain we will choose fx to be pi by 2 minus x equals 1 upon pi integral of pi by 2x minus x square upon 2 from 0 to pi. 1 upon pi by 2 into pi will be pi square upon 2 minus pi square upon 2 minus 0 So we get a0 equals 0. Now we find an. For even function it is 2 upon pi integral from 0 to pi f of x cos nx dx, which is 2 by pi. For domain 0 to pi, we again choose pi by 2 minus x. Integrating, we will use continuous integration by parts. First function pi by 2 minus x into integration of cos nx, sin nx upon n, negative sign, derivative of pi by 2 minus x minus 1 into 1 upon n, integration of sin nx minus cos nx upon n. Derivative of minus 1 will be 0, so we will stop here. From 0 to pi, putting the limits pi by 2 minus pi into sin n pi upon n minus 1 upon n square into cos n pi minus, putting the lower limit 0, this will be, since sin n pi is 0, 0 minus 1 upon n square, cos n pi is minus 1 to the power n minus sin 0 is 0 minus cos 0 is 1, so it is minus 1 upon n square. This will be 2 upon pi into this 1 upon n square minus 1 to the power n upon n square. We write an here and wipe out the evaluation. Fourier expansion of fx will contain only an. So fx equals, now putting the integral values of n, this will be 2 upon pi into 1 upon 1 square minus 1 upon n upon 1 square cos 1x, etc. plus so and so forth. This will be 2 upon pi. We can select only the first term, second term will be 0, third term, fourth term will be 0, fifth term, so and so forth. So this will be 1 plus 1 upon 1 square, that is 2 upon 1 square cos x, plus third term 1 plus 1 2 upon 3 square cos 3x, plus fifth term 1 plus 1 2 upon 5 square cos 5x, plus so and so forth. So f of x will be, taking 2 common from each term, 2 multiplied by 2 will be 4 upon pi into 1 upon 1 square cos x, plus 1 upon 3 square cos 3x, plus 1 upon 5 square cos 5x, plus so and so forth. Now let us see how to use this expression of fx to deduce this required deduction. Let us wipe this. From the definition of f of x, it is clear that fx is discontinuous at x equals 0. Here, at a point of discontinuity, say at x equals c, Fourier series gives value of fx at x equals c as the arithmetic mean of the left hand limit and the right hand limit. So f of c will be half left hand limit as x tends to c negative plus right hand limit as x tends to c positive. So at x equals 0, it will be half, which will be half into 0 plus pi by 2 plus pi by 2 minus 0, that will be pi by 2. Now by putting x equals 0 in this expression 1, it will be pi by 2 equals 4 upon pi 1 upon 1 square cos 0, which is 1, plus 1 upon 3 square cos 3 into 0 cos 0, which is 1, plus 1 upon 5 square cos 5 into 0 cos 0, which is 1 again, plus so and so forth. This will be pi square upon 4 2s are 8 equals 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so and so forth, which is what we have to deduce. Let us discuss how to find Fourier series of an odd function. Let us obtain Fourier series of function fx, x plus x square, where x lies between minus pi and pi, and f of x plus 2 pi equals f of x, implying this function is periodic. We also have to deduce number 1, pi square upon 6 equals 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus so and so forth. And number 2, pi square upon 8 equals 1 upon 1 square, 1 upon 3 square, 1 upon 5 square plus so on and so forth. Function f of x is sum of an odd function x and an even function x square. So let us denote f1 of x as x and f2 of x to be x square. We will find Fourier series of them separately. So first, find Fourier series of f1 of x, which is x. Being an odd function, a0 and an will be each equal to 0, and we have to find only bn, which is 2 upon pi integral f1 of x, which is x, into sin nx dx from 0 to pi. 2 upon pi into, here we will use method of continuous integration by parts. So first function, x into integral of sin nx minus cos nx upon n, negative sign, derivative of x 1 into minus 1 upon n, integral of cos nx sin nx upon n. Derivative of 1 is 0, so we have to stop here. From 0 to pi, 2 upon pi, putting the upper limit pi upon n into minus 1 into cos n pi, which is minus 1 to the power n. Sin n pi is 0, so the second term is 0, minus, putting the lower limit 0, 0 minus sin 0 is 0, 0 again. Cancelling pi, we get bn equals 2 into minus 1 into minus 1 to the power n minus 1 to the power n plus 1 upon n. So Fourier series of f1x will be x equals summation bn sin nx n from 1 to infinity. That will be 2 summation minus 1 to the power n plus 1 upon n sin nx. We will name this number 1. Let us wipe out this evaluation. Now we find Fourier series of f2 of x, x square, which is an even function, implying bn equals 0, and we have to find a0 and an. So first, a0, which is 1 upon pi integral f2x dx, which is x square dx from 0 to pi, equals 1 upon pi into x cube upon 3 from 0 to pi. 1 upon pi, putting the higher limit pi cube upon 3. For lower limit it is 0. Cancelling 1 pi, a0 will be pi square upon 3. Next we find an, which is 2 upon pi integral f2x, that is x square cos nx dx, equals 2 by pi into, by continuous integration by parts, first function x square into integral of cos nx sin nx upon n, negative sign, derivative of x square 2x into 1 upon n into integral of sin nx minus cos nx upon n, positive sign, derivative of 2x 2 into minus 1 upon n into integral of cos nx sin nx upon n. Since derivative of 2 is 0, we will stop here from 0 to pi. Applying the limits, 2 upon pi sin n pi is 0, so the first term will be 0, plus 2 pi upon n square cos n pi, which is minus 1 to the power n. Further, sin n pi is 0, so third term is 0. Applying the lower limit, plus 0 minus 0, sin 0 is 0, so 0 again. Cancelling pi, we get an equals 4 upon n square minus 1 to the power n. Now we write Fourier series of f2 of x, which is x square, given by a0 plus summation an cos nx n from 1 to infinity, equals pi square upon 3 plus 4 summation minus 1 to the power n upon n square cos nx n from 1 to infinity. We name this 2. By adding 1 and 2, we get x plus x square equals Fourier series of x plus Fourier series of f2x. So this is the Fourier series of function f of x, x plus x square. Now we will move to find the deductions. If we carefully observe expression 2, and in this expression if we put x equals pi, we are likely to get the first deduction. So expression 2 becomes pi square equals pi square upon 3 plus 4 times minus 1 to the power 1 upon 1 square cos 1 pi, that is cos pi, plus minus 1 square upon 2 square cos 2 pi, plus minus 1 cube upon 3 square cos 3 pi, plus so on and so forth. This will be pi square minus pi square upon 3 equals 4 times minus 1 upon 1 square cos pi is minus 1 plus 1 upon 2 square cos 2 pi is 1 plus minus 1 upon 3 square cos 3 pi is minus 1 plus 1 upon 4 square into cos 4 pi is 1 minus so and so forth. 2 pi square upon 3, but this 3 multiplied by 4 will become 12, and 2 ones are 2 6 are will become 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square plus so on and so forth, which is the deduction number 1 that we have to find out. Next we go for the second deduction by substituting x equals 0 in this expression 2. So that will become 0 square, that is 0, equals pi square upon 3 plus 4 times minus 1 to the power 1 upon 1 square cos 0 plus minus 1 square upon 2 square cos 0 plus minus 1 cube upon 3 square cos 0 plus so and so forth. This will be minus pi square upon 3 equals 4 times minus 1 upon 1 square cos 0 is 1 plus 1 upon 2 square cos 0 is 1 minus 1 upon 3 square cos 0 is 1 plus so and so forth. This will be by changing the sign. Pi square upon 4 3s are 12. Here also the signs will change. It will be 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square plus so and so forth. Now in order to get deduction 2, this one, we will add deduction 1, this one, and the expression that we have just obtained, this one. Let's swipe this middle part. So this will be pi square upon 6 plus pi square upon 12 equals, here 1 upon 1 square plus 1 upon 1 square will be 2 times 1 upon 1 square. Next 1 upon 2 square minus 1 upon 2 square will be 0. Next 1 upon 3 square plus 1 upon 3 square will be 2 times 1 upon 3 square plus similarly 1 upon 5 square plus so and so forth. Here 2 pi square plus pi square, 3 pi square upon 12 equals 2 times 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so and so forth. This will be 3 ones are, 3 fours are, and finally we will get the second deduction. Pi square upon 2 fours are 8 equals 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus so and so forth, which is the required second deduction. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel. Make constructive comments to help improve my videos. See you in the next video. Until then, keep watching Number Collage. Thank you.